that we had from the readers ahead of time. And the first one is, I've read that cleaner gear steels with fewer and smaller inclusions can provide for much increased gear life. How do you specify cleaner gear steels, and how do you know your supplier is giving them to you?
Answer that?
Yes, go ahead.
Number one, know your supplier. Make sure he can certify that he is supplying to you and can prove it. Otherwise, you can't buy really clean steel from anybody. You need clean steel, you need people that can prove that they've checked it to make sure it is in fact clean steel and meets the quality that you're asking for.
The
No, you go ahead. You were first.
okay. The rating standards give you a range of values for allowable stress, and the higher end of those values is intended to be used for what we would call grade 3 heat treat. There's a list of metallurgical qualities in the standard that identifies some of the things that Octave was mentioning about quality checks that need to be made. People saying that steel is clean is a lot different than proving steel is clean, and even steel made by the best possible modern methods can still have an occasional problem that needs to be detected. So we have to run those laboratory tests to make sure that you are getting what you paid for.
Yeah, I think I agree with Octave too. He says you need to know your supplier. I think that's almost more important than anything else. In the past, when it began that we were able to get cheaper steel from China, for example, then it was like a warranty kind of thing, or a guarantee. If you bought the steel in America and it came from Pennsylvania or somewhere, that was kind of good steel. Today, the Chinese steel manufacturers make very good steel also. And the Chinese gear manufacturers, they even distinguish between the traditional Chinese steel and the more modern, high-tech Western steel. So following the standards and having the certification and knowing who the manufacturer is, that will be that guarantee that you need.
Yeah, I think besides of the standard material tests for cleanliness or something like that, you can also use some component tests, for example, on a back-to-back test rig to get pitting life or to fruit breakage life. So you also have the experience with the failure mechanism you want to have. So you don't really specify the cleanliness of the steel, but you specify the improvement you can reach by using this special steel.
All right, thank you. Is it possible to extend gear life via specialized coatings? And has anybody done this successfully in production?
I have an answer if no one. No, you go first.
Let's say all the coat providers clearly they stipulate that they prolong the life, but you have to be very careful because very often the coat is helping the start up the first phase on running, and after that the coating is gone. Certain coatings are gone, and therefore there is no increase of life. But there may be others. But when I was asked such providers, please give me some tests so that we can add it in the software, so that you have a higher, better material value. Up to now, I never got really proved test data.
I think the coating, if we're talking about luberizing or phosphating or something like that, that's always a good thing, because you're helping the gear set to break in and the coating disappears, and when the coating is disappeared, this kind of coating, then the gear set is broken in nicely and it doesn't really require any coating anymore. If we're talking about hard coatings, there my opinion is different. I think everything that I have seen from research institutes or companies that tried it, first, it is very expensive. Second, it gives you a sub-micron or some micron layer on the surface that tends to not adhere properly. because we're having deflections, elastic deflections, and there's a skin on top. Actually, the magic that case carburized steel does has not been beaten by any surface coating yet.
I agree, there's a difference between a sacrificial coating, which is frequently done to assist getting the gears through a wear-in period, and some type of a wear coating that you think is going to stay on the parts forever. What people don't realize is the tremendous amount of pressure that there is in a gear mesh, the instantaneous temperatures that can be reached, and the deflections that occur. It's a very, very difficult environment for any kind of a coating to stay on. The sacrificial coatings tend to be softer materials like silver or copper, and they're there to ease the gear into a fully compliant surface with the mating part over a relatively short period of time. They're not going to extend the life.
One thing that I think experts must realize is they're not experts in everything. So, in anticipation of this, I contacted Bob Keller and asked him about coatings. He said that there's a thing called diamond-like coating that I am not familiar with that might increase your life. You know anything about diamond-like coating?
You know, my opinion is, if you want to be convinced about coatings, you know, coatings that are not sacrificial, that stay, run what we call a subsurface shear stress calculation. The subsurface shear stress under the surface can be so high, particularly close under the surface, that actually this flaking off effect comes. And you know, there can be the best coating in the world if it doesn't stay there. And like I said again, I'm really a fighter for a proposer of the case carburizing and all its the good things it can do. If you have a millimeter case depth, and you know you have the concentration of carbon on the surface is higher, and it fades down to the surface. Now this actually, the subsurface shear stress at the point of transition, like a millimeter below the surface, is already much lower, and the chance that this gear set survives under all the elastic deformations and some shock loads is actually higher. So the subsurface shear calculation with everybody who proposes hard surface coatings would basically open their eyes and show them if in their particular case it's possible or if it's completely illusional.
I totally agree. We also had some experimental investigations with coatings on the test rigs. Usually they decrease the coefficient of friction and therefore lead to a better efficiency. I think it depends on the failure mechanism you are looking at. If you're looking at wear, micro-pitting, or some surface failure mechanisms, coatings may help, but they won't help for tooth root breakage or even tooth flank fracture, so some surface-initiated fatigue mechanisms. So you have to be careful, and even if you are increasing your pitting lifetime, for example, this may lead to subsurface-initiated failures that you don't want to get if you coat your gears.
Very good, thank you. I realize that I failed to give all of you the opportunity to introduce yourself, and now that we have a nice crowd here, I'd say that the time is appropriate. So if you wouldn't mind, gentlemen, starting with Chuck here.
Charles Schultz, I'm the Chief Engineer and owner of the Beta Gear Service. It's a consulting firm.
I'm Octave Labath. I have a small consulting practice. I spent 39 years at Cincinnati Gear.
Hermann Stadtfeld, I'm the Vice President of Bevel Gear Technology and Research and Development at Gleason Corporation.
I'm Michael Hein. I'm a team leader flank load carrying capacity at the Gear Research Center, FZG in Munich.
Ulrich Kissling, I started KISSsoft and I'm the president of the company.
Thank you very much. I'm going to remind everybody out in the audience that you can raise your hand if you have a question you want to ask these guys. Please feel free. Just raise your hand and we'll hand you a microphone. Right now I'm going to continue with the questions from the readers. Next one is, Our company uses gear design software that was just developed decades ago. What should I be looking for in modern gear software, and what features will convince my company that the price tag is worth it?
Yeah. Hard to answer without too much publicity.
Here comes the commercial.
It's clear that already in the 80s, at least in the 90s, a lot of companies understood that developing their own software is much too expensive. You have to maintain it. The guy who is programming it will leave the company, and then you are in big trouble because your software is not up to date. So that was also the reason why I started to sell KISSsoft, because I had exactly that problem. Developing of software already in the 80s was too expensive for a medium-sized company. I would say the problem when you ask for how much it will cost, the problem is a little bit that if you would just replace the software you actually have installed, will be maybe $2,000, something like that. But today you can do much more than what you will have in your own software. You may need ISO standards, not only HMA standards. You may need maybe also product analysis, and the most important is you may need helps to improve your design. And then when see all these things which modern software bring you in helping you increase the potential of the design, then clearly the price will go up to $10,000, $50,000 per year.
We have visited this question before in the magazine. A couple of years ago, you can use our search feature in the online archives. We did an extensive survey of the software that was commercially available. One of the things we did there was talk about the fact that not every company uses software in the same way. Not every company needs the same results. Dr. Kissling's company, their software is available in modules, so if you need worm gears, you buy the worm gear module. If you don't, you don't. The problem with writing your own software is you always have that in the back of your mind. Is it right? And some of these algorithms are getting a little complex. The ability to go to a third party and know that they have people there that are working on keeping it current is a great relief to the person that only writes software every few years.
From Gleason or Klingenberg, because those are the two software packages and probably the machine part that you have decides which software you're going to use.
Will begin in 10 minutes in the solution center.
We have a question from the audience.
Question. A couple times we make helical gears to about 26 inch pitch diameter, anywhere between 4 and 8 or 9 inch pitch. A couple different times I've seen where we after grinding we measure the tooth thickness with the span size, and then we've had low backlash when we get into a simple gearbox. And finally we thought, well, let's check the tooth size over pins instead of with span. And we found that over pins, the teeth were too thick, but with span, it was within the right sizing. And using the AGMA software to convert between span size and over pin size. So what would make the teeth too thick when measuring it over pins, whereas with the span size, it could come out correct? And when I say oversized, maybe like 5 to 10 thousandths too big with the span size, or with over pin size.
The recommended method for checking helical gears is to use balls, because the span, if you think about, the tooth has a continuous curvature to it, and when you're using a pin, you can check this by using pins of different lengths, and you'll find that the measurement over pins on a helical gear will change depending upon whether you have a short pin or a long pin. The recommendation is to use balls. All the calculation methods include, for tooth thickness, include certain approximations and inverse involutes and things like that. So there's always a slight variation between the methods, but for helical gears, using pins can get you in trouble, and balls are what's recommended.
Maybe a little bit a simple answer. It's very easy to have failure in this part of software programs because span is a very, very simple formula, you know. But calculation of measure over balls and over pins is tricky. You have to be iteration, so the iteration process can be not accurate enough, and there is something a lot of people doesn't know. There may be, when you have helical gears with uneven number of teeth, balls and pin measurement is different. And I've seen a lot of software which are not knowing that. And we had a lot of discussion with people saying that also the formula in the ISO standard, they are not correct. So it's maybe also that.
Actually, I agree with basically all that has been said. However, you can make it correct. You agree with that, right? Because I just got into that with the power skiving. With the power skiving, we do also on Bevel machines. We do celebrity gears, and you need to have the tool thickness defined. Actually, I also went so far and defined the cutting tool with the pins. But with the pins in the helical, I really mean balls because there are no pins. And I would say that if you take a modern calculation, and I could actually even share the calculations that we use with you. They're taken out of the standards, but like you said, they are refined because if you have an odd number of teeth, the formula changes, and you need to consider additional things. However, if you go with the balls and you make a fixture, you put it here, the balls tend to fall off, right? The pins you can have them stay, but the balls, they want to roll away and fall off. If you make a little fixturing with the proper balls and you use the proper formula, that's the way to go. You have the most accurate, all the other calculations for span or using different length pins, they all kind of have their limitations. The balls they will provided that the formulas are accurate, they provide the real theoretical precise calculation and measurement result. And if you like, you got my name and address, we can share with you the formulas if you're interested.
I mean, maybe you check your results, certain calculation with another software, just to make sure that the values are correct. Because they may be not correct. And another thing, I don't know if you do a profile modification, if you have profile modification, then you have to be very careful because then the formulas are not correct. And then you have to really go on the 2D or 3D and measure that.
Yeah, that actually is another thing that brings me to the point that people choose the pin diameter almost like we got that on the shelf. If you choose the pin diameter very carefully, then at least by your visual observation, it seems that the pin contacts the pitch line area. That's the most safest way to go.
Thank you. Once again, a reminder, if you have questions, just raise your hand.
Measuring a helical gear with pins is not easy measurement. You need somebody who's done it before, many times.
Very good. Thank you. Next question I have is, what are the ramifications for the gear industry of the continued electrification of vehicles?
I'm always the last who wants to answer it. You wanted to answer it. Were you just about to?
Yeah, I think the demands are changing if we're going to high-speed electric engines. For example, NVH behavior might be in the foreground and not more the load-carrying capacity. So the demands will change on the gears and on the gearboxes, but in my opinion they still will be necessary also for electric vehicles.
His professor at the FCG brought his electric vehicle that starts with a T, the brand. It comes from America. The third time back to the dealership because of gear wire. That's where his answer comes from. So he has a practical application or example. Anyway, electric motors, they really like to run not at any speed. We have that in machine tools. We run them at RPM that is almost zero, and then we run
the gearboxes, but in my opinion they still will be necessary also for electric vehicles.
His professor at the FCG brought his electric vehicle that starts with a T, the brand. It comes from America. The third time back to the dealership because of gear wine. That's where his answer comes from. So he has a practical application or example. Anyway, electric motors, they really like to run not at any speed. We have that in machine tools. We run them at RPM that is almost zero, and then we run them 5,000 or 10,000. But where is the efficiency of, we're doing this electrification of cars because of efficiency, because of emissions and so on. So electric vehicle manufacturers, they have found out if they put a multiple stage transmission in combination with an electric motor, they get a way more efficient system. So does it mean they will still use bevel gears? Maybe not so much. But definitely they will use multiple stage cylindrical transmissions in the future, even for electric vehicles. There's another thing, an example I'm involved with, like the recuperation of mechanical energy into electric energy. We have one partner in the industry that builds a vehicle like that, where they're using a 4-speed planetary transmission to, when the driver takes the foot off the gas, to switch in a completely different higher ratio, such that the back driving happens with, and now the motor is the generator, the back driving happens with a much higher RPM, so that first of all, the feeling of braking is more efficient, and the electric generator works in a way more efficient level. So also that, I think a couple of sophisticated solutions that are very future-oriented show that gears will make it happen.
I used to think that we would end up with less gears with electric cars. I think we're actually going to end up with more.
Thank you.
And I think the concern about gear whine will soon be replaced by required levels of noise because of pedestrian safety. If you're going to have electric vehicles in the city, you're going to have people getting hit by cars because they can't hear them coming. And unless we want to default to that awful Vince Vaughn movie where he was going to make all the electric cars sound like they had a Hemi in them, we're going to have a little gear whine that we're going to want to put in them so that people hear them coming.
I agree with you. A little gear noise is really comfortable, right?
Yes.
We like it.
Yes.
Singing gears or happy gears?
That's what
It's the same. It's the same. What we are seeing, that maybe we will need a little bit smaller module gears, but we will still need a lot of gears.
Thank you, gentlemen. My next question. Wind turbine gearboxes fail more frequently than most of the industry are comfortable with. What are the most promising ideas to combat this?
The most promising idea is a very interesting concept that is actually developed between NASA and a university in South Carolina and the Penn State University. And that is using L. Lemansky's idea of a pericyclic transmission. I like the idea because the pericyclic transmission needs 4 bevel gears. Those are ring gears, they can be straight bevel gears. But one is internal, and we have made developments so that it can be accomplished. Very compact, a gearbox that size probably gives you about 500 kilowatt and a reduction of more than 100. So that's an idea actually that this university, the Penn State University, promotes for the application right now for the test application of wind turbines?
The wrap on wind turbines has been that they aren't looking to make their 20-year design life. They are getting better, but I do think that perhaps we need to reevaluate the 20-year life. There are very few pieces of mechanical equipment that are expected to last 20 years without serious intervention and spare parts. And to think that you're going to be happy driving a 20-year-old car as a consumer seems unrealistic. And if you're going to have advancing technology, why would you want to have a 20-year-old turbine on your or gearbox on your wind turbine? Perhaps we're going to have to reevaluate what our goals are and to have a more realistic life standard and incorporate ease of maintenance or upgrading into our design plans.
I think we had a lot of problems years in wind turbines in the 90s. And this was mainly because the duty cycles were underestimated. And at least we saw a big improvement in safety of the gears. And now it's more the bearings which are on the vehicle side are more critical. And I think we need some improvement on the bearing side, but this is a gear session, so I will not go into that.
In the last few years, always more gearboxes have been made of plastic materials. Do you think that in the near future, more steel gears will be replaced by plastic? And is there a limit for the size of gears made of plastic?
The limit is not as much the size of the gears. The limit is plastic materials are such that they move when you heat them up. And if you want a gearbox to run for a long time, it's going to get hot. And those plastic gears are not going to work right. So you're going to have to use some steel gears too.
I think we see a lot of plastic applications still more and more, but all are in a small module range, mainly for warming up problems, because smaller gears as a window lever or things like that, they just move a little bit and then they stop. I don't think that over Module 2 plastic will be in the next 10-20 years be successful, because plastic materials are not so cheap if they are high-tech, and with case carbide steel you can do things so small that we will not, I don't think that we will see there a lot of progress in plastic. But we have always more applications in small size. Everything is becoming electrical in the household and things. There we will see a lot more plastic application.
I think, Mr. Hook told us many years ago that the linear elasticity of steel is a blessing to have. It makes gears predictable, it makes deflections predictable, it allows calculations, etc. Now, in plastic we don't have the linear elasticity. We have the temperature sensitivity. We have the fact, the creeping. If the gear set is standing still under load for a couple days, you never would want to put it on a harbor crane, because the load is coming down one day. If you have a whole container hanging for a day and a night. Things like that. So my answer is, in power transmission, I don't think so. But in many other transmissions, and those are coming to the consumer products that we talked yesterday about, plastic gears will make their way.
I agree with Dr. Stadtfeld for the moment, at least. I think at the moment it depends on the application. If you have some movement gearboxes or something like that, the demand for plastic gears will increase as there are a lot of more things, electrified seats, wipers, or I don't know what. We have a lot of research projects going on plastic gears, also for power transmission at the moment. And of course, they have properties that are disadvantages, but they also have properties that may be advantages. but we need to find out how to use these properties the right way. And therefore, in the future, there might be also plastic gears in power transmission gearboxes.
Very good, thank you. I think I've got a question from the audience here.
So I have a question about gashing. So we have a machine that's very sturdy and accurate. What kind of produce quality do you guys usually see? Oh, I'm sorry. Typically we see about an AGMA 8. Is there anything better you guys have witnessed or be able to, any new technologies that have been able to go higher than that?
The AGMA 8 that you're referring to, I believe, is the Q8 of the AGMA 2000 system. We were able to get maybe a Q9 on a good day. And it really comes down to what are you trying to do with the gasher? We were basically getting it ready for gear grinding. So a Q9, Q8 was perfectly fine for us. Rapid metal removal was good. The surface finish in the root area was excellent. But I don't know that with the grinding equipment that we have today that you would really need to do any more than that.
Our only problem is that currently we have the gashing and optical capabilities. We don't have the grinding or shaping. So we have to send it out to get the shape figured out. And we have a lot of requirements to get to the AGMA 9, either Q9 or 2000. And so we're just hoping that, instead of sending it out to get shape figured out, that we can gash it.
I wouldn't have much confidence that you're going to do better than that with that. That's my experience.
Thank you.
Thank you. I think this next question is for Dr. Stadtfeld. It's a bevel gear question. Is it possible to control the curved root line in straight bevel gears or even eliminate the curve entirely?
I suppose that the curved root line refers to, the cone, the root cone, and the Carniflex method creates that cone. Actually, that is why the Carniflex method is so powerful. The interlocking or single cutter goes in the middle, plunges down at the center, and then just rolls. There is no traversing motion along the face, just plunging in the middle and then roll. It'll leave from its diameter a curve in the root. Now, in the old days, there were mechanical machines. If somebody had a machine that was called like a 102 or 2A that had a little cutter like that, or there was bigger machines that were called like 114 that cutters like that. So if you had a small gear to make and you make it on a 102 machine, you used a small cutter and you had that curve. And if your face width got wider, you might not have liked that curve, number one. Today, we're doing all of those straight bevel gears, we're doing them on CNC machines. And we're doing them not with interlocking cutters, with single cutter discs. And we have actually on almost all the machines the possibility to use much bigger cutters. So when we make a small part like that, today we can, rather than a cutter with that diameter, we can use a cutter with this diameter or even one with a larger diameter, and we get a straight root line. Now this is the answer to that we can today control, and we actually had that very often. A manufacturer buys a CNC machine before had a mechanical machine, and we were asking, do you really need that design? Is it qualified? Or could we redesign it and run it with a bigger cutter? Productivity is better and the curve in the root is lesser. And it was often done, so it is possible. However, if that's all done according to the recommendations that those older machines brought with them in their handbooks and manuals, then actually the curve in the root line has no implication on strength because the borders are higher, only the center is a little bit deeper, and it has never been proven, not with finite element calculation or test rig investigations, that a straight root line of a straight bevel gear brings more strength, root bending strength, than the curved root of a Carniflex gear. So it's nothing to worry about.
Thank you. Structure-borne noise measurement and single-flank test are today common gear evaluation methods for noise emission. Although the majority of gears which pass such evaluations are quiet, often gears are noisy, although they pass the inspections. Are there any new methods to evaluate noise?
Yes, there are some characteristics when you measure a gear which should give you good results in terms of noise or vibration. But clearly the basic tooth form is much more important, and for that you have to measure the transmission error. For example, if you do high toothing, even if you have a not so good quality on the gear, you will be lower in noise than if you use a standard gear profile. So you should decrease the transmission error and you have to use loaded tooth contact analysis to get this transmission error, and with that you can already improve or get a good design, and if then additionally you do a good manufacturing, then you should really get a good result.
I understood your question being a little bit more directed if there were new methods developed. So what does it say? Did it say FFT or single flank test, or what did it say exactly?
Okay, it says structure-borne noise measurement and single flank test are today common gear evaluation methods. And the question is, are there any new methods to evaluate noise?
So if there is something above and beyond those methods, there are methods, but they never had a breakthrough, like wavelet analysis that is similar to FFT but a different summation process. However, that case, I agree with Dr. Kissling that you look at the motion graphs. You make a single flank test and you not just run an FFT and look at a couple bars. That doesn't tell you the whole story. You look at the raw material, at the raw data, the working variation, and you see certain characteristics and then I think you said that sometimes the gear sounds quiet and loud and you don't see the difference. Yeah. Actually, you will see the difference in the single flank test, although you might not see it in the FFT. So if you're looking a little bit closer to the raw material, to the raw data, you will find the difference. However, the reader was probably asking the questions, why were we sitting on our butt and not developing something that shows that on the screen? Does really every gear engineer have to be a scientist and kind of dig in data? And that's something that we failed on our part. And I think that we're having some ideas collected at my company to go ahead and come up with a future generation of single flank test that gives you on the screen as how could you call it, quality data, or some physical data about the properties of the bevel gear set, which then would be not only amplitude, frequency, which would be additional characteristical elements that are linked to noise.
Just a reminder, if you have a question from the audience, just raise your hand.
Just a quick follow-up to the single flank issues there. What is holding the industry back from utilizing single flank testing more effectively? Doesn't seem to be a whole lot of single flank testing going on.
Can you say that again?
Can
he repeat it?
What is holding up the industry from doing more single flank testing? The equipment doesn't seem to be available, and there doesn't seem to be too much conversation about the utilization of that test. It seems to be a very functional way to check a load, even under some load characteristics.
It is a very functional way. Some people even call the single flank test the absolute measure, a kind of an absolute measurement. There's nothing lost, it's a quasi-static, it's not, dynamics are filtered out and so on. I have to say in bevel gearing, bevel and high put gears, it is almost an industry standard. Every manufacturer that produces a little bit higher quantity than 5 bevel gear sets a day, maybe 500 a day, they use single flank test and structure-borne noise I have to admit in many cases, because the structure-borne vibration analysis is so much faster, that those manufacturers often using in their gear lab for developing the gear set the single flank test, then they try to run structure-borne noise analysis, correlate the two, and in production they only do the structure-borne because it's so much faster. But the single flank test has become also faster because we don't need that hunting tooth anymore. You know, the hunting tooth means you need as many pinion revolutions as you have gear teeth. So you wait forever on that machine that has the slow RPMs. But we can actually now already with 2 or 3 pinion revolutions predict what's going to happen. Those things are done, but I agree in cylindrical gearing we don't see that much a single flank test. And the reason is probably the cost of adequate single flank test equipment. I think the double flank test is the next closest to a single flank test, and you can see it at the booth where the company that I'm working for, we have to be uncommercial here. You can see at the booth a little machine is a tabletop that size, actually that makes a very fine a double flank test, a very fine and with very significant answers to the question of what makes my noise and what is my gear quality.
Thank you. My next question is, in gear grinding, is it always recommended to grind the root fillet?
There are many people who will refuse a gear if you grind the root fillet. The answer is no.
If you get five gear engineers in a room and ask this question, you're likely to get 6 different opinions. Because somebody's going to weasel their way into having it both ways. Some people like the predictability of always grinding the root, so they know that they've always got that condition. Other people prefer an unground root because they like the mechanical properties that are there from the compressive stress from the carburizing operation. The biggest problem that we have, and an area of great research effort, is what happens when you're halfway in between. And the transition between a ground flank and an unground root, when you don't have enough protuberance on the tool, or there's an area where you have what we call a grind step. This is an area that I know Dr. Kissling's done a great deal of work with his software on to try to help people evaluate it. But that's the reason there's 2 distinct camps on it, and we're in so much trouble when we end up in between the 2 camps.
It's the same question in bevel and high-point gears. Only the answer might be a little bit easier. In aircraft, worldwide in all Western countries, government regulations demand that the roots are crowned as long as it's a power transmission part of an aircraft, not an actuation, but a power transmission. So that takes that away. Now, in automotive truck, I'm of the opinion, and that basically echoes what you say. I'm of the opinion that the root should not be crowned, but that bears a lot of dangers in them. Because saying the root should not be crowned, you might have a really lousy transmission between the flank and the root. You get interferences. Interferences cause noise, they can cause micro cracks, they can rip off a tooth and you think it was the bending, but it really wasn't the bending, it was a geometrical failure at the tooth form. So what we have developed is, in order to kind of even that out, or in order to smooth that out, the answer to that question, if you're making the decision to not grind the root, then you're using what we call the semi-finish strategy. It puts top rem towards the root of the flank, and the top rem really blends out into the root fillet. Now the following grinding operation is such that the edge radius of the grinding wheel blends with that root fillet radius. So the top rem actually is ground away. Only the grinding wheel load, the grinding load, chip removal load, in the top rem section is lower because that's a critical section for burning. And then we have this fading out, and that can actually, the machines have input items where you can set the grinding wheel a little bit over to balance out where the blend is better, drive and coast side, so to optimize that. and the bottom of the root is uncrowned. And another remark with the properties of the root. Yes, I also think that you can put, those fins sometimes, fins and steps, by grinding the root out and just plowing it a nice fillet radius channel, you actually cause invisible notches in the structure of the material. It looks nice, but it has bad physical properties after the grinding. That's why often aircraft people do the soft manufacturing and they dust with a grinding wheel through the bottom before they go to heat treat in order to avoid this invisible notch.
I think that can help to, if you have a critical design for tooth root breakage. But if you really want to avoid tooth root breakage, you should also consider shot peening or super finishing or barrel finishing. If you do a fully ground tooth root, you cannot get a grinding notch, so that's quite positive. But you should keep in mind the residual stresses, the case carburized layer, if you have a case carburized material that you remove while grinding the tooth root.
What I hear from our customer is that when you only grind the flank, you do not know so much about grinding. If you go into the root area, you have more problems. It's very delicate, so you need more know-how and maybe more time, and it will cost you a little bit more. That's why very often we see that, I would say, 90 to 95% are just grinding the flank, and then or using protuberance or just having to check for the grinding notch.
Very good. Thank you very much. We're getting close to the end of our time limit here, so I'm going to ask if anybody from the audience has any more questions. And if not, I have one more. And that is, have there been any successful applications of 3D printing for gears? If so, what industries and or applications?
I know of that Airbus Industries uses for actuation purposes several Inconel printed gears, actually bevel gears, spiral bevel gears. And they're using them already for a while, they're flying already in the plane.
We had some experimental investigations on 3D printed gears with cooling channels just below the active flank surface. Well, they did not work quite well because the load carrying capacity of these 3D printed gears was really bad. So the cooling channels did not help to increase the efficiency.
You know, I heard from people from metallurgists say, the problem is my customer likes to case carburize, and that is difficult with the 3D printed material. However, you know, we're living in 2017. Let's look what happens in 2025 or so. I believe that the 3D printing, as the density gets better and more different materials are available that can be used, that during the printing process, you can use a different core material and a different surface material. And maybe one day it's possible to replicate maybe at least 60–70% of all the advantages that today a case carburized gear presents. So we should be open-minded to this technology, I believe.
Very good. Thank you all. That's going to bring our session to a close, and I would like to thank all the experts here for their time and their expertise and for helping us learn a little bit more about gears. If you could help me give them a round of applause.
Thank you.
Thank you.